and moving on to the next session, which is building production-ready serverless applications and engineering lessons beyond Hello World apps. So we're taking a shift from security, AI, now to serverless, right? So at this point in time, allow me to welcome Belinda joining us all the way from Mombasa or Nairobi? Which one, Belinda? You have to unmute.
Okay, hello everyone. Okay, my name is Belinda and I am excited to be here actually. And thank you, Kampala DevOps, for this opportunity to join you guys and have this conversation. So before I begin, I have one question. Kindly, maybe, I don't know if the attendees can access the chat.
Yes, there's a Q&A chat, so they can be able to type something.
Okay, for me, I love interactive sessions. So I have one question that maybe attendees can drop their answers there. I have one question. So who here has ever deployed something and immediately started praying? I have many times. You do a prayer and say, please God, let this work. And I don't have to go back into debugging or anything like that. So let me know in the chats. So today we are going to work on reducing the amount of prayer required in production, but I am not promising magic because most of the times these things do happen. Even if you think you have done your best, you have secured the application, it's reliable, you have done everything by the book, and sometimes your production may break or you may get those calls at 2 a.m. So today we are just going to have that conversation, like how do you make that application or that system from it works in your computer to it works in production. So yeah, I'll be sharing my slides in a bit.
There's some feedback for you in the chat.
I did for my first application. That's nice. I have done it.
The QA.
Okay.
So a couple of people have been saying prayers every time they deploy to production.
Where are my slides? Here they are. Yeah. Okay, let me put them on slideshow mode. Okay, so today I want us to look at what happens after that first successful deployment you have made. How do we make the application secure? How do we deploy changes consistently? And how do we know what's happening when something breaks? And how do we design the system so that one failure doesn't bring everything down? And perhaps one of the most important questions that we should be asking ourselves when we are building production-ready applications is, can somebody else operate and maintain this system without maybe you intervening if you're the one who is doing it, without you intervening, or maybe somebody else requiring your input or your help? So today we are not going to be doing a live demo. Instead, we are going to use the architecture, engineering decisions, and know how to make trade-offs and real development challenges to walk through how we move from something that simply works to something that we can actually operate. So let's start with a very simple question. When we say it works, as an engineer or as an architect, one thing that you're supposed to ask yourself is that enough? Okay, like let's say I have built an application and I tell you it works. What exactly have I told you? I have probably told you that under the conditions I tested, I got the expected result, right? But I haven't told you if the application is secure. I haven't told you whether it's repeatably deployable. I haven't told you whether I can see what's happening inside, and all those aspects that come in to make a productive system. And this is the distinction I want us to carry throughout this session. Working software and operable software are not necessarily the same thing. I'm going to give you a simple analogy of a restaurant. So let's say if I can cook one really good meal for one person, I have proved that I can cook that meal. But that doesn't necessarily mean that I have built a restaurant, right? We have so many people who are good cooks, but they don't have restaurants or they cannot operate a restaurant. Why? Because a restaurant has to serve customers consistently. It has to manage access. It has to handle busy periods, and it is how to know when something has gone wrong. It needs processes other people can follow, and it needs to keep operating tomorrow. So that's the difference we are exploring today. We are moving from, can I make the application work, to, can I operate this application reliably? And that requires us to change the questions we are asking, or questions that we ask when we are building systems. So I think it's the next slide. Yes. So we are going to be moving from this shift of from can I build it to can I operate it, by looking at different aspects when it comes to building applications: security, reliability, deployment, observability, recovery, as well as maintainability. So each question narrows the gap between a demo and a system someone can depend on. So when we are building something for the first time, our questions tend to be very implementation focused. Which service do I use? How do I connect this? How do I get the API working? How do I deploy it? So once the application becomes something people depend on, the questions starts changing, because if it's a system that people are depending on, you have to look at something called security. You have to know who can access this application or this system. What can each component do? So if something is compromised, how much damage can it cause? You also have to look at reliability. What happens when a dependency fails? What happens when messages are delayed? And what happens when something doesn't respond? So you have to look at those aspects so that you can know, have you implemented it? For example, when it comes to security, if you don't implement the security part, for example, you don't implement something like least privilege, it means that sometimes you will give a blast radius access of resources, between resources, or even between persons accessing the system. And a lot can go on. For example, someone may land on something that they are not supposed to see. And we know sometimes people can be so dubious, even if they're working in that company. If they land on information that they're not supposed to be accessing, it can really become critical, and they can do a lot with that information. Let's also look at deployment. You ask yourself these questions: can I make changes consistently? And or does deployment depend on someone remembering exactly what they clicked or configured? So all of these are some of the questions that we ask when we are trying to build a production ready systems. Now, going back to our restaurant, cooking one meal is the beginning. Running the restaurant means building the systems around that meal. So let's take one common business scenario and use it to reason about that architecture. So what actually needs to happen before we respond to the customer? A customer has placed an order, maybe in an e-commerce application. That sounds like one action from the customer's perspective, right? I have gotten into this e-commerce website, for example, Jumia, and I have made an order. So, but for me as a customer, I just know I have made an order, but internally, several things may need to happen, right? So we need to accept the order. Maybe the system also needs to process payment, update inventory, and also maybe it needs to send notification. So now here's the architectural question. Do all of these things need to happen before we respond to the customer, or they have to happen separately? And I will explain that in the next slide. So this is where architecture starts, not with which AWS service do I like, but with what actually needs to happen synchronously and what doesn't. So for example, if a customer comes to you and they need you maybe to develop for them an e-commerce system, you have to listen at the client's needs and what they want to happen when a customer places an order. So from there, you will know what you are dealing with, and you will make your choice between using a synchronous system or using an asynchronous system. So asynchronous means we can accept the work and allow another process to continue independently. But for synchronous, it means that each and every process has to wait for the next process has to wait for the previous process to complete for the work to continue to the end, okay? So back to our restaurant. When you place an order, the waiter needs to accept your order, but you don't need the waiter to stand at your table and personally supervise every activity in the kitchen before telling you, yes, we have received your order. Actually, that would be a very strange restaurant, right? A waiter comes, you place an order, they go, right? They go to make sure that your order is being processed and it's being prepared. But just imagine a waiter standing by your table, and then after some time, they tell you, yes, we have received your order. It's very strange, right? So let's see what happens when we design the system around that idea. I am going to use an example of one of maybe a project that I have worked with before. And it's an event-driven serverless architecture. So let's walk through this architecture from the request all the way through the downstream processing and see how it works. So this work it has a front end and a back end. So the front end is developed using Angular and hosted on Amplify and CloudFront and WAF for and Cognito for authentication. So the API is where the customer request enters through API gateway. Now, API gateway gives us the HTTP interface into our application. Now, that request invokes Lambda, okay, where we execute the application logic without managing servers ourselves. Now, that's the part where serverless comes in. Then after the order, after Lambda has been invoked, it sends an event. So this event is received by event bridge. This one, event bridge. And now, instead of keeping the customer waiting while every downstream operation finishes the application to publish an event, so the event bridge acts as an event routing layer. How? The important idea is simply that we are using event bridge. So the important idea is that the producer of the event doesn't need to tightly couple every consumer. So event bridge receives the order, and it has different consumers here. We have different Lambda consumers. We have the payments consumer, we have the inventory service, and we also have the notification service. And we have introduced also SQS. So this means that each and every service is working independently. Payment doesn't have to wait for inventory to be updated, and it doesn't have to wait for notification to be sent. So it means that the customer can make an order and the payment is done. as the other consumers complete their work. So nothing has to wait for the other to be complete. So now the work of SQS is introduced here in front of the consumers. Why? A queue gives us a buffer between producers and consumers. So if a consumer can't process work immediately, the work doesn't necessarily disappear. It can wait in the queue and be processed later. So this also allows different consumers to scale independently. Now, around the application, we also have concerns that aren't really part of the business flow itself, but they are essential to operating the system. We have Amazon Cognito. For authentication and identity, we have WAF here, and it's for protecting or protection of the application edge. We have IAM, and it's for permissions between AWS resources and making sure that we implement least privilege between resources. We have the AWS KMS here. So it's for encryption and key management. CloudWatch for logs, metrics, and operational visibility. So notice that the architecture isn't just a collection of AWS services. So each component exists because we are solving a particular problem. And there's an important trade-off. So yes, we have picked these services because we feel they will solve this kind of problem that the client is trying to avoid. But at some point also, when we are picking these services, we have to make some trade-offs, right? Because it doesn't mean that because we have picked this service, it's the perfect. No, it's perfect for this job, but it also has its own limitations. So for example, we have a trade-off like eventual consistency. This means that once we make parts of the system asynchronous, we accept that everything may not be updated at exactly the same moment. The order may be accepted now, yes, while inventory processing happens a little later. So that is called eventual consistency. You don't see the updates at the same time compared to the synchronous system. Synchronous system is because you are waiting for each process to be updated. So you can see everything at the same time. But when it comes now to a synchronous system, you have the events are happening at different times. So you can't expect to have consistency in terms of updates at the same time. So the system can still be correct, but correctness is no longer defined as every component must finish before the customer receives a response. And I want us to make something very clear here. So event-driven architecture is not automatically better. If the business operation genuinely requires an immediate response from a dependency, make it asynchronous just because we can would introduce unnecessary complexity. So you have to look at your client's requests. Maybe the client will say, I don't care. I just want a system that just processes everything sequentially. So you will have to go for synchronous, because sometimes you may explain to a client and they will not want to know. Maybe they have their own reasons why they want a particular, maybe their system to operate in a particular way, right? So you have to be very intentional in terms of listening or to maybe a business problem from your client or even what they need. So architecture is not about using more services. It's just about making the right boundaries. And one of those boundaries is the boundary between synchronous and asynchronous work, as we have seen. And this is what I mean by synchronous system. So on the synchronous side, the request moves through multiple operations and the customer waits for the chain to complete. So a customer comes, makes an order, they go to checkout. So payment has to be processed. After payment processing is complete, we move to inventory update. The inventory is updated. Then we move to email, maybe notification. After there is an email notification has been made, then we receive a response. So that is synchronous. Every step waits for the other to be complete. Now, the problem isn't that synchronous processing is bad. I'm not saying that. Don't misquote me. Synchronous processing is just often exactly what we need. As I have said, a client may insist they want a synchronous system. And for you, maybe you think asynchronous is the best, but a client wants asynchronous. So you have to do what the clients need. So the problem is allowing unnecessary dependencies into the critical path. Now, on the event, now let's look on the event-driven side. We jump on the other side of the wall. Now, we keep that critical path VINA. What is the critical path? The critical path is the work that has to complete before we can give the caller the response. So on the event-driven side, we keep that critical path VINA. How? We accept the order, we publish the event, we respond. The downstream consumers continue processing. This is how it happens. The customer makes an order, they go to checkout, order is accepted, and they get a response. They may get a notification. Then the event bridge starts processing the other request, payment, inventory, notification. Nothing is tied to the other. They're just working independently. So process payment, it's independent. Inventory reserve or update stock is independent, as well as notification, send an email or alerts is independent. Nothing has to wait for the other. So decoupling improves resilience and independent scaling, but it introduces eventual consistency, as we have seen in our last slide. So now a notification service doesn't necessarily have to determine whether the customer gets an order acknowledgement. Inventory processing can have its own scaling behavior. We have seen that. And payment processing can have its own retry behavior, completely independent from the other consumers. Now, but we haven't magically made the system simpler. We have changed the kind of complexity we have. So now, for example, introducing SQS, yes, we have this time for buffering, maybe a request has been made and there was an error and the process doesn't have to come tumbling down because there was an error. The request is hibernated maybe in a queue to run at another particular time. But now you have introduced other complexity like retries, duplicate messages, failed consumers, ordering, eventual consistency, and monitoring. And you have to know how to handle all of this. So, for example, if an event is delivered more than once, because sometimes the system may receive, it may duplicate an order, okay? So our consumer shouldn't accidentally charge the customer twice. So that means we need to think about idempotency, which is designing an operation so that processing the same request more than once doesn't produce an incorrect result. So making sure that if a customer comes and makes an order, if an error happens and that order runs twice, we don't have to charge the customer twice. So decoupling doesn't remove complexity. It puts the complexity in places where we can manage it. And that brings us to the bigger principle behind all this architecture, the architectural trade-offs. So as I have said earlier, architecture is not about choosing the best service. It's just about choosing the right trade-off that you accept to make. So for example, let's look at Lambda. Lambda gives us managed compute and automatic scaling without managing servers. But we work within execution and runtime constraints. Lambda has a maximum of 15 minutes After 15 minutes, it dies. Okay, so if it dies, and maybe, for example, your workload has to run for 2 hours, it means it has run for just 15 minutes. The rest of the 1 hour, 45 minutes, you have to know how to handle it, okay? And that's where maybe now you can look at other ways to work with still Lambda, but make sure that even if it's a workload that runs for 2 hours, it still continues. And therefore, you can introduce other services like step functions, of which we're not going to look at that today. We are going to look at what we have here today. So now, Event Bridge. Yes, we have gone for Event Bridge, and it will help us to decouple producers and consumers. But now we are working with asynchronous behavior and eventual consistency. And as I have explained earlier, eventual consistency is where you don't receive updates at that particular time. Like, updates happen later. They don't happen at the exact time, okay? So you have to wait for the updates to happen at a later time. Then we have SQS. Yes, it will give us buffering and failure isolation. But now we need to manage queue behavior, retries, and consumers. You have to think about that. And maybe if you think about retries and queue behavior, sometimes you will end up introducing another service like DLQ. Then we have DynamoDB. DynamoDB provides us with a NoSQL database that can scale significantly. We don't have to intervene, but we need to design around access patterns rather than treating it like a relational database where we can freely query whatever we want later. So when someone asks, so for example, when it comes to trade-offs, when someone asks you, why did you choose this service? You don't want your answer to be because AWS recommends it. No, there is no perfect service that AWS can tell you, oh, today use this service, is the best. No. You want to be able to explain the requirement, the constraint, the decision, and the trade-offs that you have made, okay? So in our restaurant, if we decide to prepare certain things in advance, for example, chop the onions in advance, tomatoes in advance, maybe we chop our cabbage in advance, and other things like meat, we get faster service during busy periods, right? If customers are just coming and maybe you're a restaurant that serves fresh food and customers keep on coming, it means that you prepared early enough. You don't have to start chopping onions when customers have come, look for tomatoes, a customer wants chicken, that's the time you are running after the chicken so that you can slaughter it. No, you have everything prepared, okay? But as you have these things prepared, they can go bad fast, right? So you have to manage storage and freshness for the food or the ingredients that you have prepared. So that is the trade-off. Yes, we'll prepare early, but you have to think of, maybe I need a bigger cooling, like a freezer, where I can store these ingredients that we have already prepared so that they don't go bad before our customers arrive and they start, maybe we prepare them food that is not good. Now, there is rarely a perfect architecture. I will tell you, there is no perfect architecture, and there's no day you will say that I have maybe created a perfect system or a perfect application. The only thing that exists is an architecture whose trade-offs fit the problem that you are solving. So how do we actually think through those decisions? Good architecture answers why, okay? So this is probably maybe I don't know if it's the most important part of this conversation, but let's start with our requirements. We want the customer-facing response to be fast. What are our constraints? Payment, inventory, and notifications. They don't necessarily need to block the initial acknowledgement. So what architecture decision follows? We can decouple those downstream processes. What's the trade-off that we are making? We are accepting asynchronous processing and eventual consistency. So what's the operational consequence? Now we need retries. Yes, we need to handle failure, monitoring, and potentially idempotency. Now that is engineering thinking. So notice that nowhere in that process did we begin with, I really want to use Event Bridge. We started with the problem. Which problem are we solving? Okay, and which service can fit on this to solve this problem, and what are some of the trade-offs we are making? So it's the same thing in our restaurant. I'll still use our restaurant so that we can flow with that mental model. So if the problem is that customers wait too long during lunch hour, you don't immediately say, let's buy another oven. What will you do? You first understand where the bottleneck actually is. Maybe the kitchen is slow, maybe ordering is slow, maybe payment is slow, or maybe the menu has too many options, okay? So the solution comes after understanding the problem that you are having. So now let's apply the same thinking to security. So if this function is compromised, what can it touch? I will look at this on two different angles or two sides of the wall. We have a blast radius. That is, we have given excessive permissions. Maybe, for example, you have your Lambda and you want it to access some resources, and you end up giving it administrator access, okay? So giving a Lambda administrator level access is convenient. It also means that if that function is compromised, we have potentially given the attacker an enormous blast radius, which means they can also access other resources within your system. If your system has S3, DynamoDB, RDS, Secrets Manager, IAM, or any other resource within your system, it means they can easily access it, okay? So when we talk about blast radius, we are talking about how much of the system can be affected when something goes wrong. Now, if we implement least privilege, let's go to the other side of using least privilege. It means giving a workload only the permission it actually needs to perform its job. So if this Lambda, our Lambda here, only needs to read from one DynamoDB table, why should it have permission to delete objects from every S3 bucket in the account? It shouldn't, right? So if you give it an execution role, you have given it an execution role, that is the least privilege. So you give it specific actions. That is, I'm giving you access to DynamoDB table, but you can only put item and get item from DynamoDB table, and that's all. So it doesn't get connected to any other resource in the system. So we have given it a small blast radius. So back to our restaurant again. So do we ask yourself in the restaurant, does the person preparing salads need the key to the cash office? They don't, right? Does the person handling payments need to access the storeroom? Probably not, okay? So you only give them, if maybe it's an accountant, they only have access to their office, the accounting office. They don't need access to the storeroom. They don't need access to the kitchen. The same to someone who is in the kitchen, that is a chef. Why should you give a chef access to the account office? Why? Maybe it will only give them access to the storeroom because they need to go and get cooking items or ingredients that they need. So different responsibilities require different access. So least privilege isn't about making permissions complicated for the sake of security. It's about reducing unnecessary access. So we don't design security only for the happy path. We design it for the moment something goes wrong. So security controls what the system can do. Now, let's talk about controlling how we create and change the system itself. Kindly, if you have any questions, feel free to drop them in the Q&A or chats. If there's any question that I need to address now, maybe I can pause for a minute. Is there any question that I need to address? Okay, then I will move
the
on.
chat is clear.
Okay, thank you. So now let's ask ourselves, I have created this system or this application. Now, can I recreate the environment tomorrow? If I need the same kind of application or the same kind of infrastructure, can I create it again tomorrow? And that's where now we come and to look at infrastructure as code. So let's say we have built the infrastructure manually. And this, I mean that maybe you have an AWS account and you want to create or to build, how is it called? Maybe a static website on S3, or maybe even another system. So we create an API, we create the Lambda, we create permissions, we configure queues and set up monitoring. And everything is working, okay? Now imagine we need to recreate that environment again. Can we? Maybe yes, maybe no. So yes, you may remember what you clicked yesterday, but come back to that system after 6 months, after 1 year. Do you trust your memory enough to remember what you exactly did, or maybe the configurations you made? Maybe after 6 months, 1 year, you may not even remember, okay? So that means now we have a problem here and we have to solve that problem. And how do we do it? We solve that problem by using infrastructure as code. Simply meaning we define infrastructure in files that can be versioned. That means if you have made any changes, you can follow through your commits, your Git. I hope we have developers here. So you understand by what I mean by Git add, Git commit. So you can come back to your commits and know what you really made changes on, maybe yesterday or maybe 3 months earlier. Now, it also means that we can review what we have built and apply it consistently. So I'm going to use one of the infrastructure as code tools, and that is Terraform. So Terraform becomes the mechanism for defining that infrastructure. So how does it happen? So here we have Terraform as our tool. We create code, okay? Then we version control that code, store and track infrastructure. We review it, maybe we peer review, and also collaboration means that my teammates can be able to know what we are doing through the state file, as well as plan, preview changes before applying. And then now we apply our changes in a controlled way. After making the, after doing apply, our resources are provisioned and managed now on AWS. So I am not teaching you Terraform. I'm just using Terraform as an example. There are other tools, infrastructure as code tools, but Terraform is one of the major or common most used tool. So the bigger engineering principle is that infrastructure should be repeatable. It should be reviewable and it should be recoverable. Again, let's go back to our restaurant. So if the only person who knows how the kitchen operates is the chef who opened it, you have a people dependency. This is how. Because if something happens to the chef, maybe they fall sick one day and they're not able to come to work, it means that that restaurant will be closed down on that day, right? Because there is no one else who knows what is supposed to be done. Same to you as a developer, an engineer, okay? Or an architect. You have created this system. It's awesome. You have done it perfectly and it's working. Then down the line, you may get greener pastures and move from that company to another company. Or maybe even you get a teammate. They may not be able to exactly know what you did because everything is configured manually. But if you did it through infrastructure as code, they can be able to review the code and know, actually, this system, it uses EC2, it has the 3 buckets, it has, these are the configurations for the IAM, everything, okay? They'll have a picture of what was done. Okay, so that's what we are trying to achieve with infrastructure as code. So we don't want infrastructure to exist only because someone remembers how it was created. We want it to exist because it is defined. So once infrastructure and application code are defined, the next question is how changes move into the environment. And that's how I introduce the next concept, which is CI/CD. So what happens when we need to change the system? So let's say I have made a change. Maybe I fixed a bug, and or maybe I changed a Lambda. What happens next? So we push the changes, okay? We validate the changes. Maybe we look at formatting, we look at analysis, we do the security scans, and then we test it. So we run automated tests, the unit, the integration, etc. Then that it's built, that is the application package, we package the application and build the artifacts. Then it's deployed to the targeted environment. If it's Azure, if it's GCP, or even it's the AWS. So we have deployed it, right? And we are sure it's working. And that doesn't stop there, okay? So we need also to observe. This is where I want to challenge one common definition of CI/CD. So CI/CD isn't simply I pushed code and it deployed automatically. Deployment is only one part of the process. So after deployment, we need to observe what happened. Did the deployment actually work? So that's why we do the monitoring. Did the deployment actually work? Did error rates change? Did latency increase? Are downstream consumers processing messages? So what we learn becomes feedback for the next change, because when it comes to applications and systems, changes keep on happening, right? So that's where we will do that through the observation here. So we deploy, observe, learn, and improve. It goes, we start back here again, okay? So if our restaurant introduces a new process in the kitchen, we don't assume it's successful just because we have implemented it. We watch what happens during service. If orders slow down, we adjust. If errors increase, we investigate what is going on. So automation without feedback is just faster guessing. So, and feedback is very important. You really need to know what has really happened. You need the evidence of what has really happened or what error are we facing, so that you can be able to solve that or to debug efficiently without doing debugging blindly or not knowing what you're really doing. And that brings us directly to observability. So when something breaks, what can you see? So now imagine something has gone wrong and a customer says, my order didn't work. Where do we start? Okay, where do we start? So the request may have gone through the API, gateway, then Lambda, then the event bridge, then SQS, and then the consumer. That's a distributed workflow. So observability is about giving us enough information about the system internal behavior that we can understand what's happening from the outside. So in practical terms, we are interested in signals such as logs, metrics, and errors. So CloudWatch gives us a place to collect and inspect many of these operational signals. So monitoring often answers, is something wrong? Maybe you are seeing warnings or alarms on your dashboard. Observability helps us now to investigate. Why is it wrong? Why am I getting alerts? Why am I getting errors on my dashboard? So in our restaurant, imagine customers are complaining that orders are taking too long. Just knowing that orders are slow isn't enough. So we need to know, as I said earlier, is the kitchen slow? Is ordering slow? Or maybe the payment is really slow and it's making these orders to delay. So is one particular station backed up? So you have to, so that's the difference between knowing there's a problem and having enough information to investigate it. So, and once we have those signals, we still need a disciplined way to use them. So, yes, if you investigate, most of the times you'll get the root cause, and it will give you a direct information of this is the root cause. Maybe one of your Lambda, maybe you did a change and one of the Lambda consumers maybe died, and that's why maybe you are not getting notifications. So you'll be able to know, I don't have to re-engineer the whole Lambda again. Maybe I have to look at the notification consumer, okay? Now, after you have investigated and you have your root cause, now you get into the debugging process and not guesswork, because now you have your logs, you have your metrics, and you know where the problem is. So you're not working blindly on resolving the problem. So this is where, okay. So, and we have all been tempted to do the we have all sometimes been tempted to, if you hear maybe there's an error, you start maybe doing changes or debugging blindly. And that's why I introduce this system, like 7 steps on how you can go through debugging. So you have first to identify the symptom. So you have to really know what is actually happening. Then you look at the evidence, you go to the logs, the metrics and errors and what they are showing. Then you draw your hypothesis. So based on the evidence above, what do I think is happening? Okay. What do you think is happening? Maybe the CPU is full or something like that. Then after that, you test. What can I check to confirm or reject that hypothesis? So you do your series of tests, maybe that you created to test a particular error if you get it. Then you identify the root cause. So after doing the test, you'll be able to know the root cause. So what actually caused the problem? Then you go on now to fix it. So what change addresses the cause? Maybe you need to tweak the code a bit, or maybe add something, or even maybe remove a particular part of the code. Then you verify, did the fix actually work? So you have to run that work again and see and verify if you are still getting the errors. Now, so you notice that the symptom and the root cause aren't necessarily the same thing. Okay, so symptom is what you have identified as the problem, but now the root cause is what is causing that symptom. So for example, a Lambda timeout is a symptom. The root cause could be a downstream dependency, inefficient processing, an incorrect timeout, or even a permissions issues or something else. So if I immediately increase the timeout without understanding why it timed out, I may simply be making the symptom take longer to appear, because I have done it blindly, because I have said, oh, it timed out, let me increase the timeout. But you don't really know what is the problem. So by increasing that timeout, if it's the error, it means that you have just prolonged or make the symptom to longer wait for it to appear. So, so if just that one change of prolonging the symptom, it means that you have created a patient failure, and you don't want that to happen, okay? So serverless introduces additional debugging. Challenges because the workload is distributed and managed across services. So packaging can behave differently after deployment. Service integrations can behave differently from what we expected. And IAM permissions can prevent a function from performing the next operation, and failures can occur downstream from where the original request started. So the place where you see the failure isn't necessarily where the failure began. And this is exactly why production systems don't always look as clean as our architecture diagrams. So the theory may be clean, but reality isn't. So this is the part that is most important to acknowledge. So architecture diagrams are clean. You have created this architectural diagram, and you know, if I do this, everything is going to work perfectly. So everything is neatly connected. You know, you have done a good job. The arrows are behaving, the service are cooperating, the application does exactly what we expected. But now real systems are less polite. They will give you trouble. So let's look at local versus cloud. So something can work locally. You are just coding and testing everything, it's working locally. But the minute you ship it to cloud, the deployment may fail. And that doesn't necessarily mean the code is bad. So the environment, the configuration, permissions, or even integration may be different. So when services communicate, they have contracts. So the expected request format, the expected response, the permissions, the behavior when something fails. So, and if we can see a symptom in one place while the actual cause exists somewhere else. So these aren't edge cases we can completely eliminate. So they are part of working with distributed systems. So these are exactly the kinds of things that make cloud engineering interesting to me. And you can have a beautiful architecture diagram and still spend an afternoon asking, why is this thing not doing what I think it should be doing? And then you discover it was a permission configuration or even an integration issue. So the architecture diagram tells us how we expect the system to work, right? Observability and debugging tell us how it actually behaved. So after all of this, what do we actually mean when we say something is production ready? Let's see. So what does production ready actually mean? It does not, let's define production ready. So it doesn't simply mean the application deployed successfully. It doesn't mean we used serverless. It is definitely doesn't mean we have a lot of AWS services on the architecture diagram. All that is wrong. Production readiness is about whether we can confidently operate the system. Can we control access? This is our production ready system, but we have to ask ourselves, can we control access and reduce unnecessary permissions on this workload? Can the system handle failures without unnecessarily taking everything down? Where is my cursor? Oh, here it is. Observability. Can we understand what is happening? Automation. Can we consistently make changes? Scalability. Can the system handle changing demand? And can the system handle change? We sustain the cost of operating it? Maintainability. Can another engineer understand and work on it? And those concerns interact. So for example, adding more observability can improve reliability, but it can also introduce additional costs. So adding more decoupling can improve resilience for your system, but it can also increase architectural complexity. Then increasing permissions can make development easier, but it increases security risk. And that's why production readiness is not a checklist of services that you are using. It's a set of engineering trade-offs that you have to make. So I want to turn this framework into something you can actually use. That is the checklist. So before you call it ready, ask yourself these questions. Can I secure it? Can I recover it? Can I observe my workload? Can I deploy it once, twice, or even 3 times without having overhead or maybe a headache of the configurations that I made? Can I scale it? Can I afford it? And can someone else maintain it? So this one is particularly important because if the system only makes sense to the person who built it, we have created a dependency on a person. That's why I said, for example, in our restaurant, if it's only the chef who knows the recipe and everything about the restaurant, it means that if something happens to them, that restaurant will be shut down. Another person cannot run that restaurant again successfully. So the same thing happens in engineering. So good systems are not just understandable to their creators, they are operable by a team. So if you are working on a project right now, choose one of those questions. Which one would be hardest for your current system to answer? Maybe you can give us answers. I know here we have builders, we have people who are working on personal projects or even workplace projects. Kindly tell us in the chat box if you are looking at what you're working at the moment, which one would be the hardest question among these to answer in your current system? So when we are learning cloud or getting something to work feels like the finish line, right? You have created this system or this workload and it's working and hooray, you have done a good job. But you have to ask those questions that we have gone through, and you have your infrastructure has deployed, your API works, and that's a great achievement. So we should absolutely celebrate that, right? But that's where the next set of questions begin, and we have looked at them in terms of security, reliability, observability. How can you recover them? How can you scale them? And if given that you have a teammate, can they be able to maintain that system if you are there or not? So those questions are what take us from simply building something to engineering something. So, and that's why my talk was about don't stop at the hello world. The hello world I meant at don't just deploy and say it's now working and you can relax. No, now that's just know that that's where the engineering begins. Thank you so much, and I would be happy to take your questions now.
Wow, that's what I can say, Belinda. It's this was beyond even serverless.
Thank
Yeah,
you.
this was beyond serverless. This I would say is the playbook to go into production, right? This is something I wish like I would have known in my first year of DevOps, right? Because you talked of blast radius, you talked of ClickOps, you talked of a number of things that were like a light bulb moment, like every time, because this is beyond serverless, right? You're looking at you're looking at continuous integration and continuous delivery of software, but even you're looking beyond that, we need to monitor. You're looking at, the principle of least privilege. There are a number of fundamentals in this, right? You need to even focus on, like when you're engineering, look less at the tools, but look at answering the key fundamental questions, which I think
Yes.
is key to engineering real production systems. And I think from experience, I can really testify to that, right? And I would
Thank
say
you.
this was a light bulb session, in my opinion. I don't know what probably
Yes.
people think in the chat. Yeah, please share your question. So there is one from Boya. Does CloudWatch show errors automatically, or there's some configurations to do before I can troubleshoot there? And she says, very great talk. Thank you, Belinda.
Okay, I've seen. What is the question again?
Does CloudWatch show the errors automatically, or is there some configuration to do before I can troubleshoot there?
Okay. One thing with CloudWatch, sometimes you can see the errors, maybe the logs immediately. Sometimes it doesn't work the way you expect. And there's this issue of CloudWatch. For some time now, they have been having this like degradation, and it doesn't work maybe the way as an engineer would expect it to use. And sometimes people tend to use, how will I call, like outside tools, like other monitoring tools outside AWS for proper observability. Yeah, but you need also to identify the kind of logs and what you want to observe with CloudWatch in your system. So you have to do some configurations, of course. Yes.
Oh, yeah, that is truly insightful. And the other bit is, I think an earlier comment, production is the hardest part, and the most important, this AI can help in doing most of the development work. And I think I can also allude to that going to production tends to always be really different from the usual. Running on localhost is easier
Yeah.
than going to production. Yeah.
Yeah.
Any other feedback? If you have any questions, please type in the Q&A section. There's one from Juliet. Apart from Grafana, which other tools can you use for monitoring and observability inside the application?
For me, mostly I have used CloudWatch. I think because it's inside AWS and it's somehow reliable for me to work with it. But I can say I haven't like experimented with other outside tools for monitoring and observability, but it's something that I would be intentional to try out and give my feedback later. Yes, thank you.
Yeah. But yeah, I would say Belinda, you truly cooked. I think this sometimes we don't need to go into the technical demos, but we need to dive into the concepts underlying to architecting right for production. And I think you've truly done that well. You've really delivered. And I
Thank
think
you.
from the feedback and engagement, I think we are all convinced. I think at one time I was talking with a colleague and I told her we can run applications just using lambdas and API gateways, and we shall spend less of what we spend on cloud. And she doubted that, but I believe after this session, she will believe it, that we can run something on serverless. I think when you're talking about the synchronous and asynchronous, and I think those slides really delivered. Yeah, but thank you so much. Thank you
Thank you.
for delivering such an insightful talk from all the way from Kenya. Yeah, community supersedes borders. Yeah. Without further ado, thank you, Belinda. So at this
Thank you.
point,